and the vortex here V with gamma vortex. And I want to know the effect of this vortex on that point. So this vortex will induce, here is U induced, the induced velocity. It is function of the coordinates of the point and the vortex, right? This is what? It's gamma over 2 by R in between. This is R between the 2 points. Okay, this magnitude in what direction? In this direction. It's perpendicular to the radius. So this is U induced as a vector. So in the direction perpendicular to R, I will write it like this. This is a unit vector E in the direction perpendicular to R. Okay, let's get it as in X and Y. So this is delta X between the 2 points. This is delta Y. Maybe this is theta. So this is also theta. So we'll create a function. We'll create a MATLAB function. Let's call it bios of R. This function takes what? Takes the xy coordinates of the point and also xy coordinates of the vortex and returns the induced velocity. Okay? So let's construct this function. Well, from here the induced velocity is gamma over 2 by R, and I need what are the two components. What's the x component, what's the y component? Well, the x component we multiply by negative sign, and y component by cosine. So this is negative sign, and the y component is cosine. What is the sign of this theta? Sine theta is delta y over R. So this is delta y over R, and this is delta x over R. So this function is so easy. So actually it's gamma over 2 pi R squared, and here are the components, negative delta y and delta x. So this function, when you get xy the point, xy the vortex, get delta x please, get delta y please. So get the R squared, which is delta x squared plus delta y squared. And here is your U induced, the output of the function is, we will do it for a unit strength. So it's 1 over 2 pi R2, so R squared, times negative delta y and delta x. So this is for a unit strength, unit gamma. We can multiply the result afterwards by the strength of the vortex, if we know its strength. Any question about that? We will use this function over and over again. We'll use it many times.
So why are we computing U induced in this case?
Why we are computing U induced?
Yeah.
Because here, remember how we apply, what's the main equation? The main equation is the V normal equals something. The right hand side is known. What's the left hand side? The left hand side should include our unknowns. So these V normal, what are these V normal? What are these V normal? It's the one due to your gamma bounds. So we'll do what? At each point, we will compute the induced velocity normal to the surface due to all the bound vortices, right? So we'll call this function n times or n plus 1 times. Okay? Not only that, for the unsteady case, we will get at this point the induced velocity due to all bound vortices and due to all wave vortices, right? This is what we're going to do right now. So here, let's construct the first equation. V normal 1 is equal to, at the end of the day here, is equal to V normal 1 motion, which is known. What is V normal 1? Well, it's summation over all vortices, right? Vortices V, we give it the index V. What? The U induced, right, of this point 1 and this, all these vortices, right? What is this U induced? If you want to write it in our language, it's biosavant. But anyway, let's put it like this. The induced velocity of each vortex on the point P1, okay? This is normal to the surface or not yet? It's not yet. So we need to dot it with the normal to the surface. A unit vector normal to the surface. So the geometry, you have to tell me what's the normal to the surface. Okay, we'll define it in a minute. So now this is V normal due to all vortices, right? Yeah, let's expand that. So this is summation, or J equals 1 up to, we have how many bound vortices? How many vortices on the wing? How many vortices? How many unknown vortices? How many unknown vortices? N plus 1. We have 1 at the trailing edge, right? So our biosavant of, we give it the name of the point, XY point. XY of the vortex, right? So let me here discuss something. If you have, let me do it up. Here's good. If you have this guy, this is your airfoil at some instant, and I'll take one panel, and I will zoom it like this. We agreed to assign a vortex at each panel, okay? Where do you suggest to put it? Assume this panel by itself is a flat plate. Where do you suggest to put your vortex? Should I put it at the leading edge? Should I put it at the trailing edge of the panel? The middle point of the panel, where? Where do you suggest to put it?
The further part.
Very good, the quarter core. Why? Because this is indeed the center of pressure, the center of circulation distribution for a flat plate. If you consider this guy as a flat plate by itself, so this is the high point. Very good. So, okay. We will put our gamma here, we'll call it gamma bound, and this, the coordinates of this point, the quarter core of each panel, we will call it XY bound, for bound vortices. XY bound, okay? And when we apply the equation itself, the V normal relative is 0. The V normal is equal to the V normal due to motion. Where should we compute the normal velocity? Should we compute it here at the quarter core, half core, at the trailing edge? Where do you suggest to compute it? It's as if, where do you take your angle of attack? 3/4, very good. So at 3/4, so if this is your D spacing of your mesh, then this is D over 4, and this guy is 3D over 4. So here we induce the condition that the V normal relative is 0, okay? We will call these points control points. So these are the points at which we have bound vortices, XY bound. This point we call it control point, right? So the coordinates we call it XY control point. Okay, so we work with our equation V normal of the first control point. So this is XY1. Or if you want to be accurate, it's XY control point of 1. Okay? The first point. So what I'm trying to say is that x, y bound is a matrix like this. It has two columns. All the x's, all the y's of the quarter pole points. And x, y control point, again it's similar. All the x's, all the y's of the three quarter poles. And we should have also a theta, how each panel is inclined with the chord actually. So let's do this here.